Welcome. In this unit 6 we look at parametrized surfaces, and to get prepared to it we look first at polar coordinates, a coordinate system in the plane. So here we have the xy plane, and we have seen that we can describe a point with two coordinates x and y. Maybe this point has the coordinates 1, 1, but we can also use angles and distances to express this point. And let's just introduce this angle theta and the distance r. So theta is a Greek symbol, Greek T. And you all know this picture here. You can now read off x and y from r and theta. So what we have is that x is equal to r cosine theta and y is equal to r sine theta. So that's the relation. That's just the definition of the cosine and sine. And in this case, what we have is point 1, 1. So 1, 1 in Cartesian coordinates. That goes over into, we can write r theta, which is in this case equal to square root of 2 and pi fourth. So this data here also describe this point. So we can also go backwards, and given x and y, we can find r and theta. Let me just write that down here. So we have r is equal to the square root of cos x squared plus y squared. We always take the positive square root here, so this is bigger or equal to 0. And theta, here I have to put that into a little bit with a grain of salt here. It's the arctan of y over x. Right, that's the y over x and then the arctan. But that's only defined up to pi. So we have to be a little bit careful. Usually what we have with arctan, the arctan usually goes from minus pi half to pi half. And so this is with a grain of salt here. But we usually, when we draw if we draw the point, right? For example, here, if this would be 1/2 and this would be square root of 3/2, then we can read off the angle here. So in this case here, this would be 90 degrees plus 30 degrees, 120. And so the distance here is, in this case, it would be 1. So we can by drawing the picture, we can often kind of read off the angle theta. In space, we have to describe a point with 3 coordinates, but we can also do that with angles. That's what Euler did. Let me just make a picture here. That's the x-axis, this is the y-axis, this is the z-axis. And what we do is we reuse this angle theta, which we have already seen in polar coordinates. Let me just write that here. So this is the angle theta. Let me just assume here, maybe this is so this is theta. And now what we also use is an angle which goes from the z-axis to the point. So if you have here that point P, which is x, y, z, in space, we have a second angle which we call theta. That's phi. This is this angle here, phi. Let me just write that here, phi. This is a little bit of Greek alphabet here. And so this angle phi goes from 0 to pi. So let me just write that down. So theta goes from 0 to 2 pi. Let me just put smaller than 2 pi, because if you reach 2 pi, we call it again 0. And phi goes from 0 to pi. So phi, that's the angle from the z-axis to the point, goes all the way from 0 to pi. And then the theta goes like that, the phi goes like that. And then we have a third parameter which we need to describe the point, and that's the distance to the origin. And we call this rho. So this is another letter here, rho. Distance to the origin. Now we want to find a relation between x and y and z and phi, theta and rho. Let's just do that by drawing two pictures, two important pictures here. So one picture is if we look from above. So if you have x, y from above, what we see here is the angle theta. We see the angle theta very well. So this is the point P, and this is the angle theta here. We see that angle theta very well. We also see a distance r. That's not the rho. That's just the distance to the. That's the distance to the. That's the distance to the. Let me just draw it here. That's the distance to the z-axis here. That's not a coordinate here in this part. It just helps us to find a relation. And then we can read off x and y here, x and y. So that's the picture from above. And the point will sit here somewhere in space. Now we have also a nice picture is when we look from the side. So when we look from the side here, so this is the z-axis, and this is the xy plane. So we can also call this r because we see here the r value. And then we have here the point P. We look from the side, and we see here the rho very well. That's actually the rho. And we also see the angle phi very well here. So that's the angle phi. Now we can read off from this, we can read off r, and we can read off z. So let's just write below here what we get from this picture. We get that x is equal to r cosine theta. That's what we have seen before. And y is equal to r sine theta. And in this picture, what we see is a relation between r. We can see r and theta. So r is equal to, we see that angle here again. And that's a right angle. So you see that it's the r sine. It's the r is the rho sine phi. And the z is the adjacent here. So z is equal to rho cosine phi. So these are two important pictures. This is from above and this from the side. From the side view you see this, from above you see this. And now we can read off the relation between x and y and z by put things together. So we see that x is equal to rho sinus phi cosine theta. Y is equal to rho sinus phi, that's just r sine theta. And finally, z is equal to rho cosine phi. Now this is extremely important. So that's what you have to actually see. How I remember it is always kind of, I have these pictures in my mind, and I also know that this r here is my key. So that r here. So that I just know this is r cosine theta, r sine theta, and here this is just the z, which I read off from this picture here. So these are spherical coordinates, and we can do examples, right? So if you have, for example, the point 1, 1, 1, what are the spherical coordinates of this point 1, 1, 1. So when I do that, I actually just make quickly this picture here. I look from above, and so when this is x and y, and then I look from the side, and I see this is x is 1, 1, so that's here. So I can actually read off this angle. I can read off the angle theta here, which is theta is equal to pi fourth. And here I see, when I look from the side, I see the r here is square root of 2. So that's square root of 2, and that's 1. And so I can read off that angle here. So that's the angle phi. So one possibility is to actually say this is maybe arctan of square root of 2. Something you can just compute with a calculator. And then we can have also the rho. That's actually something we can do independently, and maybe I just write it here. Rho is very important. That's just the distance to the origin. That's x squared plus y squared plus c squared. So rho in this case is square root of 3. So this point has the coordinates pi fourth, this number arctan square root of 2 and square root of 3 as the spherical coordinates. Okay, that's all about spherical coordinates, and now we go to the parametrization of surfaces. Okay, we have already seen graphs of functions of two variables. So if you have z is equal to fxy, like for example x squared plus y squared, then this is a surface which this was a paraboloid. So for every x and y, we have a z value. So it's a very vertical line test, right, to see whether it's a graph. This is a graph. And we can immediately write down the parameterization. It's almost tautological. It's very, very easy, but one always forgets the easiest things. So what we can say is x, y, z is actually just x, y, fxy. So in this case, it is equal to x, y, x squared plus y squared. So that's also a parametrization. That's a parametrization of a graph. Let me take the opportunity to, in this section, this kind of short section, also to get the general picture of a parametrization. So what we have is, in general, we have some domain here in the maybe uv. Usually, kind of you use different variables, u and v, s and t, theta and phi, x and y, whatever you want to use here as your, and then we have a map R, and then we get the surface S in space. So this is the map, right? This map here gives us R of u of v, gives us x, y, z. And what we have is we have different grid curves. We have grid curves like that. And when v is constant, that gives you maybe curves like this on the surface. Or we get different grid curves when we take u is equal to constant. We get grid curves maybe like that. So that's how a computer draws a surface. So these can be arbitrary functions of u and v. So these can be arbitrary functions of u and v. And this is also called the UV map. What you see in computer graphics, for example, when you are drawing on a surface, maybe this is a face, maybe this is an avatar you want a face, and you want to draw a face on it. Right? You take the face, and that face becomes a face here. So what you can do is, you don't like to draw in space. It's hard to draw in space, but it's easy to draw in the plane. You want to map this over. So these are also called textures. in computer graphics. When you have scanned an object and you get back a grid which tells you the geometry, but you also get the textures which tell you how you paint different parts of the surface. Okay, if you want to parameterize a surface of revolution, that would be a surface of revolution. When you turn it around, it's the same surface. A sphere is a surface of revolution. This is a surface of revolution. This is a surface of revolution. A surface of revolution is when you turn it around, it doesn't change around an axis. This is a surface of revolution here. And what we are given here is the distance to the z-axis. Let's just call this g of z. So that's equal to r. So we have r is equal to g of z, and we can now describe this. So we have z here. Maybe z is equal, goes from a to b. So z goes from a to b. This is z, and this is theta. And so what we can say is we can look at the grid curves here also. So we have the grid curves. So these curves here, when theta is equal to constant, they go into curves like that on the surface. So these are these grid curves, and then we have also grid curves like that. If z is constant, we have just the same height. We see these curves. That's how a computer draws a surface of revolution. But how do we translate this? What is the relation between x and y and z and theta and z? So what we can do is start with the easiest one, z. There's nothing to think about because z is the parameter already, that's z. And then we have a r cosine theta and r sine theta. So g of z cosine theta, g of z sine theta. So this is the parametrization of a surface of revolution. Parametrization of a surface of revolution. And in this case, maybe that would have been g of z is equal to maybe 2 plus sinus z. That would be kind of an example like there. You see the radius changes when you go up and down, it changes. Surfaces of revolution. Let's look at a couple of examples. I will continue a little bit, but that's kind of the lecture, the core lecture I wanted to do. But let's continue a little bit with examples. But surfaces of revolutions are very beautiful, and the grid curves can be very beautiful here. This is kind of an example of a surface of kind of a surface of revolution, which is just kind of an unusual parameterization. This is a donut, and you will see a donut in the lecture, and I like this particularly well here. This is a nice way to draw this donut. Donuts are everywhere. They're in bagels. Surfaces of revolution are everywhere. Fruits. So first of all, I want to draw your attention to the 4 examples which we have here. We have already seen the parameterization of a plane. That's something we have covered last time. I didn't repeat that. Parameterization of the sphere. Essentially, it's the spherical coordinates. This is essentially polar coordinates with a z component. That's called cylindrical coordinates also. And that's something we have seen just in the unit 5 when we have graphs of functions. So you can focus on that. 90% of the cases are like this. But some of the cases are not like this, like the donut, for example. This is an example you see also in the homework. The donut is an example where we have kind of the donut is a surface where we have different coordinates. So usually what you do is, let me just write you down what we have, x, y, z. So what we have is we have a radius r, maybe 2 plus cosine phi, cosine theta, then 2 plus cosine phi, sine theta, and sinus phi. So how you can understand this is also using polar coordinates. That's r cosine theta, r sine theta. And somehow what helps here is to look also from both sides. Look at here r and z, and also look at x, y. So if you look at this donut, here it kind of has two circles. And in this case it has an inner circle, he has an outer circle. So a general point on that donut here, this point here, is maybe a point here. And so what we have is, I did not explain what phi is, but phi is not the same angle here than the phi angle which we have in spherical coordinates, but that's phi. And the theta angle is here. That's the theta angle. Let me just make it yellow again. So what happens if you change theta, you go around like this in the donut, like this. When phi changes, you go around like this. You rotate around the donut differently. So let me just see, this is an example which is not of this type. It's of a new type. So this is the torus, the two-dimensional torus. And think about this as r here, and this is z. So you can read off here, actually this is x and y, you can read off x and y, and here you can read off z and r. R is this, which is equal to 2 plus cosine phi. So this distance here is cosine phi. This is sinus phi. Just this is phi here. Just by this, looking at this triangle, you see cosine phi, sinus phi. You see 1 here. And when changing phi, you are rotating around like that. When you change theta, you rotate around like that. So it's a very special surface, and it cannot be explained with these 4 examples, or basic 4 examples. But we have also the grid curves. So we can draw the grid curves of the phi constant or theta constant. And these are not the grid curves of this, what you see here, but we could also parameterize it using, so that it has more interesting grid curves. So that's example 1. That's just kind of a difficult example, and you see that in the homework. Let me just take some simple example, like how do you parameterize x squared plus y squared is equal to 1? So that's a cylinder. So you cannot parameterize it as a graph, right? Because it's not a graph, there is no x and y then z. We cannot do that. We can also not a spherical, it's also not a plane. So surface of revolution is really the only thing which works, and that's it means actually that the radius is constant. The g of c is equal to constant. So we can immediately write down the parameterization. So this is r, which is 1 times cosine theta, 1 times sinus theta, and that's so this is the parameterization. R is equal to, so g of z is equal to r, that's equal to 1 in this case. So that's example B. Let's look at another example. Why don't we look at this one, the one-sheeted hyperboloid, x squared plus y squared minus c squared is equal to 1. The one-sheeted hyperboloid. It's also a surface of revolution, and if we write this like in cylindrical coordinates, we can say r squared minus c squared is equal to 1, or r squared is equal to 1 plus c squared, or r is equal to the square root of 1 plus c squared. So that's our r. Once we have the r, we can immediately write down the x, y, z. So this is the square root of 1 plus c squared cosine theta, square root of 1 plus c squared sine theta, and equal to z. So that's the parameterization of the hyperboloid. And we will look at much more examples in class. See you then.